Hello and welcome to week two's remediation topic, which is on nuclear chemistry and atomic structure. So remember, we've already talked about these things, so this is very much review. So you can always look back at your own notes. But remember, there's three basic particles that make up an atom: protons, neutrons, and electrons. Protons are positively charged, neutrons are neutral, electrons are negatively charged. Protons and neutrons have about the same mass of about 1 atomic mass unit. Neutrons are a smidge heavier, but they both have a mass of 1 atomic mass unit, and they're both in the nucleus. And then remember, the electrons are in the energy levels and electron clouds outside the nucleus. And so on your periodic table, there's, some basic information that we have for each of those elements. There's the symbol, there's the name, there's the average atomic mass or the atomic weight, and there's the atomic number. And so the atomic weight over the average atomic mass is a weighted average, and we'll talk more about that in a couple minutes. And the atomic number is equal to the number of protons. All right. And so as we look at those different types, there are ways of representing specific atoms of specific elements with specific numbers of protons and neutrons and electrons. And so sometimes this is called the isotope, or nuclear notation. And so it has some basic parts. It has the atomic symbol, which is the abbreviation from the periodic table. And then on the left side, there are two basic numbers. One is the atomic number, which is the number of protons. And the second one is the mass number, which is the protons plus the neutrons. And that mass number is always a whole number. The important distinction we need to make is that the mass number and the atomic weight or the average atomic mass are not the same thing. Okay, that average atomic mass is always a decimal number because it is an average of a lot of different what are called isotopes. Whereas the mass number is always a nice whole number because it always is just adding up the protons plus the neutrons. And so if we take a look at kind of a typical example, this is a specific type of carbon atom. And this carbon atom, we look on our periodic table so that we can figure out what the element is. We look and see, all right, this bottom number, remember, is the atomic number, which is 6. That gives us the number of protons. Remember, the number of protons, it's the identification. It distinguishes one type of element from another. If you change that number of protons, you're making a new element. Because there's no charge, and if there were a charge, it would be written up here. But because nothing's up here in this upper right corner, we know it's a neutral atom. And so that means the protons and the electrons have to be the same because the charges have to balance out. There has to be the same number of positive charges as negative charges. And we can count 1, 2, 3, 4, 5, 6 protons and 1, 2, 3, 4, 5, 6 electrons. To get the number of neutrons, we have to take the mass number, which is the protons plus the neutrons, and subtract it from the atomic number, which is the number of protons. So 12 minus 6 gives us 6 neutrons. Okay. If this element had a charge, we would have to adjust the number of electrons. So if the charge is positive, we have to subtract electrons. Okay. If the charge is negative, we have to add electrons. Okay. To get the right number of electrons given the charge. So, for instance, if we look at some examples, and so when we look at these, keep in mind that there's two kind of notations here. There are the nuclear isotope notation we just talked about, but there's also this different notation. This notation makes use of the name or the symbol and the mass number. So this notation doesn't give as much information, so you have to look up more on the periodic table. Can't really use it too well with ions because there's no place to put the charge, but this number, if you see something like this number is the mass number. So if we look at some of these, that bottom number is always the atomic number, so we know the atomic number is 11, and whatever the atomic number is, that's also the number of protons. The mass number is always this top number in the nuclear notation, or it's this number in this other type of notation. It's this number. So in this case, 24. The neutrons, if you have the nuclear notation, it's easy because you just take the mass number minus the atomic number, top number minus bottom number, 24 minus 11, and we get 13. For the number of electrons, as long as there's no charge written here, then the protons and the electrons have to be the same number so that we have a neutral atom. Okay. You can come back to the screen and kind of try some of these if you want to on your own. If we have something that has a charge, like notice this example here, it's a sodium ion in this case. Notice that the mass number is different. It is still sodium, so it still has an atomic number of 11, so we need to write that into the symbol. And so whatever the atomic number is, that's also the number of protons. The mass number is always that top number, so in this case it's 23. Right. And the number of neutrons is always the mass number minus the atomic number. So 23 minus 11 gives us 12 neutrons. Now, the number of electrons, if this were a neutral sodium atom, there would be 11 electrons to balance out the 11 protons. But it has a +1 charge. So that means if the charge is positive, you have to do the opposite and take 1 electron away. So in this case, we would have 10 electrons, which means that we have 1 more proton than electron, 1 more positive charge, 1 extra leftover positive charge, and that makes this an ion with the +1 charge. Right? And we see that in our symbol. So again, these are some examples that you can do if you want to kind of come back to the screen and just try some extra examples. They're here. If we look at some specific element like carbon, we see that, okay, this carbon has 4 different types of atoms. They're all carbon. Notice their atomic number is all the same, but they have different mass numbers because they have different numbers of neutrons. We call these isotopes. So same element, same number of protons, different numbers of neutrons, and so they have different masses. All right, so they have different numbers of neutrons. Okay. So they're all still carbon. They're just, the nucleus is a little bit different because some of them have more neutrons and are therefore heavier than the others, but the protons are the same, so it's still carbon. And so you see that difference again in that number of mass numbers. Now, if we take those isotopes, and again, kind of look at them a little more closely, we see here is again 3 of those isotopes, and notice all of them have 6 protons, but there are some extra neutrons in the heavier isotopes. So the protons don't change, but the number of neutrons do. Okay? And so if we take those isotopes and we want to represent the element carbon on the periodic table in terms of the typical mass of a carbon atom, we have to take into account all of the different isotopes that exist for carbon when we represent that its mass on the periodic table. But we have to take into account that some of those isotopes, some of those forms of carbon, are more common than others. And so we can't just do a normal average, we have to do what's called a weighted average. So, which is a type of average that takes into account that sometimes you have situations where all parts of the average don't factor in or don't contribute the same amount to the final average. Your grade in a lot of your classes is a weighted average. Not all parts of your grade factor into the same amount to your final average. They have a weighting factor. Okay? Quizzes, exams, term papers, right? Now, you add those weighting factors up, it adds up to 1 or 100, which it should, but quizzes in this case for this grade, right, are weighted much less than exams and term papers. Okay? And so to get that final average, we have to take the average score in each of those parts, multiply it by that weighting factor, and get that that weight, that part of the grade. And then the final average is then the sum of all 3 of those different factors, or 82.1%. Now, when we want to get the average for mass for an element on the periodic table, and we want to calculate the average atomic mass, we have to do a weighted average. But it's a little bit different. Same process, it's just we call things a little bit different. In this case, instead of having an average grade, we have the mass of each isotope. So these are the masses of the 3 isotopes of magnesium to a high degree of precision. Do we need this degree of precision in our calculations? No. And instead of a weighting factor, we have an abundance. And so this means that out of all of the isotopes all of the atoms of magnesium that exist, about 79% of them are magnesium-24. And then, right, the process is the same. We have to take that abundance, which is our weighting factor, times our average grade or the mass to get the portion of our final mass that is that isotopes contributes. Now, one thing that's misleading, and that's kind of a misprint in this, right? When you have these abundances, these are in percents, you need to divide by 100. So So take the abundance as a percent, divide it by 100, multiply it by the mass of each isotope, get your answer, and then you have to add them all up to get your final average atomic mass. There's no dividing by 3 or anything like that. Abundance as a decimal times the mass of each isotopes, get an answer, add all of those results together to get your average atomic mass. Okay. In part 2 of our remediation lectures, we're going to talk about some topics in nuclear chemistry. Okay, so look forward to seeing you